I will be taking you through the finite element analysis exercise. And if you remember, I told you this last time as well. All the details have been already uploaded on the content section of your D2L folder. Okay. So first of all, you should download this example from here. Before I do that, I think what I'll do is I will also cast my screen on your screen so that it is easy for you to follow. So sorry, the software is still loading. So while this is loading, I will just download this part. Okay, I've already discussed with you, so I've already uploaded there a template, right? So you should actually download the template as well for the report. And then there is also this step-by-step instructions in the PDF that I have given you, okay? So if you miss any steps, then you can always follow it from the book. But because I'm also recording the session today, so hopefully you'll be able to also follow it later on using the recording. So basically, the problem that we are solving is the same problem that I have already discussed with you in the lecture session. Okay. So now I will also cast my screen on yours so that you can easily view this. Okay, is that now visible? Okay, so you can move it on a side if that interferes with your actual making of the model, but I would like you to follow this step by step. So you can see here the part is same as the one that we have already discussed in the lecture session using hand calculations, for our hand calculations. So what I will be doing now is I will be solving the same problem using a few different approaches. Actually, we will be comparing 4 different approaches using the finite element analysis package. Now, so basically, this is your part file, and this is then the loading shown, and this is what we solved in the class. For your individualized group cases, right, you have a different set of values that you have to use, okay? And that is already uploaded on the D2L, and it is available in this lab report template document, okay? So this shows the force that you will need to use. So depending on whether you are group A, B, or C, or D, again, you're free to choose which group you want to join, but make sure that you join one of these. So the main difference will be the material and the load that you are going to consider in each of these cases. The rest of the procedure will remain same. So let's now do this problem step by step. So for the finite element analysis, the first thing that you need is, of course, your part file or the geometry. Now this can be made in the regular way that you make any part file on the SolidWorks. So that's why I have skipped that part and I have directly imported the part file. But keep one thing in mind, that you always have extra features in the geometry that may not be important from an analysis point of view. So you may or may not actually want to replicate them, okay? So what I will be doing is, as a first step, whenever you are going to start a new study, you'll go into the simulation tab, right? So this is the simulation tab that you can also see on your screens. So you click on the simulation tab, and then you go on to the new study icon. When you click on the new study icon, you will be able to give this analysis a certain name. Again, this name can be anything, but it is better to use the names which are describing the kind of analysis that you are doing. In this case, because we will be comparing the different types of the meshes which I'm showing here, so I will use the same name as the book has used, and I will call it as draft mesh and default size. So right now you don't know what this default draft mesh and default size means, but very soon this will become clear. So I'll call this as draft mesh and default size. Okay. So once I have named this, because I will be later comparing all of these results. Okay. So now second thing that I want to mention over here is the type of the analysis. Right now we are calling this as a static analysis, because if you remember in this course I told you we are using the assumptions of statics. We are considering the part that we are analyzing for stresses to be in equilibrium, right? So we are not going to solve explicit or implicit dynamic equations directly for our model. Rather, we are going to solve the equations of statics. So that's why this is a static model. The second option over here is use 2D simplification. In many large parts, you can actually use 2D simplifications. And what does that mean? That actually means that in the background, then basically the software will be solving the 2D version of the equations. Okay? But if you remember, I showed you in the lecture session the full 3D stress and strain tensor, as well as the stiffness matrices related to that. Yeah, and so basically for each point where the software does the computation, I'll show you the mesh. So on each of those nodes, the software will be basically solving that equation F is equal to KU, which is the fundamental equation for your finite element analysis, and it will be solving that essentially. Okay, sorry, I thought it was in this set of slides. It is probably in the other set of slides. But anyways, you remember the 3D matrix that I already shown you. So with that, then we will not use the 2D simplification right now, and we'll just solve the whole problem as a 3D problem. So I'll just say okay. After this, the first thing that I'm trying to do on the model is to apply simplification, because there are certain features which are there and which are important from the actual part that you make, but they are not going to affect my analysis too much, and if I keep them there, they will just make my analysis more difficult. Okay, so for the computer to actually mesh in these narrow zones. So to do that, I will select these fillet features at the end, and I will select all of them one by one, or I can actually select them by using this fillet group that I had created. Sometimes we don't have the groups already created in the geometry, and in those cases you can actually select these individually. And once you have selected all of those features that you want to remove from your analysis, you just simply click on this, and you have this option of suppressing these features. So as soon as I click on the suppress button, you can see that the software removes them from your view, so that now the actual geometry that you are going to analyze for your stresses is shown. Okay? So this is the part then we will analyze, and it is exactly comparable to the part that we had made over here and were analyzing, okay, using hand calculations. Right. So now the first step in your any of finite element analysis is that you basically assign the material. Without assigning the material, the software will not understand the relationship between the stress and the strain, and because the software only uses the full constitutive equations to solve for the stresses and strain at each nodal point, it will not be able to give you the stress results or any of the other results unless you give it the material definition. So to give it the material definition, we will right click on the material icon, then we will say apply edit material, and we will actually then select the material. In this case, the material that I am using is AISI 1020 steel, and you can see the properties of this material are already given in the software database. Okay. Now, in practical situations in real life, many times you want to have a material which is not necessarily available in this. So, in that case, you can actually define your own custom material as well. Sometimes your properties may be slightly different based on the from the given properties based on your manufacturer's recommendation. So, right now you cannot change this. But if you want to change these properties, what you'll need to do is you'll need to copy this over, and you will need to take it into the custom materials portion of your library, and then here you can create a new category, and then basically within that category, so you can say my custom metals. Okay. So once you create this new category, you can actually right click and paste the material. Now, once you have pasted the material, now you can see instead of gray they have become all white, which means you can now physically alter these values. Okay. So you can actually physically change this value. So for example, if I want to change this to 1.92, I can do that, and this value will be then saved. Right now, because we are using university computers, if you click save, it may throw you an error, which simply means that you do not have access to the drive. Okay. In those cases, what I recommend is that you first save the model to OneDrive. Okay. Because if you have it saved in the OneDrive, then the material library will also be saved on OneDrive, and you will be able to make the changes accordingly and save it. Otherwise, on the university computers, you may not have access to the drive. Okay. So you'll need to save the library first to OneDrive. In my case, because I'm not really interested in making any changes, so I will not really save these changes, and I will say don't save it for now, and I'll go back and I will apply edit the same material which is available in the database. I'll just make sure that the units selected are SI units, and then I will say apply. In this case, our material is a linear elastic isotropic material, so this definition also does not need to be changed. So I will click on apply, and I will then just simply close the bar. You can see here now in this where the name of the part is given, in front of it is now the name of the material that you have chosen. Okay. So now that means your material has been assigned. If this name does not show for whatever reason, it means you need to redo the definition, and you will need to reassign the definition. Okay. So that's the first main step. Next step will be to define the boundary conditions and apply the loads. So we will do that. I'll just pause the video at this point and restart the recording.